Hi, I will be talking about a potential groundbreaking application of CMOS terahertz camera for implementing them in a broadband terahertz spectroscopy system. This CMOS terahertz camera will provide an additional degree of freedom that will enable the measurements with high accuracies than presently done, and will also enable dynamic measurements as compared to the currently available standalone spectroscopy systems. The Terahertz camera was developed at the Institute for High Frequency and Communications Technology, also known as IHCT. At IHCT, we tried to create compact, reliable, silicon integrated terahertz systems that are widely accessible. Our broadband terahertz camera, as shown here, is one such example, capable of operating at broad frequency range all the way from 100 GHz to well above 1 terahertz. This lens integrated camera can be applied in different applications. In this work, we are evaluating this capability by investigating broadband far-field emission pattern of a widely used terahertz photomixer source operating between 100 GHz and 1.3 terahertz. We are implementing a compact antenna test range method that overcomes the problems faced by the conventional far-field measurements of limited power and low sensitive detectors. Remember, the far field distance also scales as the frequency or as 1 over lambda, the wavelength. Combine it with the 1 over r square decay of the power. The far field at higher frequencies is more challenging to say the least. Alternatively, in Cater, the symmetrical integrated hyperhemispherical lens on the camera provides the necessary functionality of transforming emitted radiations into quasi-plane waves at short distances with a beam waist at the focal plane array located on the other side of the planar side of the lens. As you see here, the conventional measurement performed at the near field distance, we can observe the radiation related to the evanescent field, which decay and cease to exist in the far field distance, as you can see here in the far field measurement. Now, when we compare the far field measurements performed with the conventional measurement as well as the Cater, they resemble very much with each other. The Cater based measurement reveals much more details due to higher SNR. So once we have validated the far field measurements with Cater comparable with the conventional far field measurements, what we have done is now we have undertaken far field measurements using Cater at the entire broad frequency range of the photomixer, all the way from 100 GHz till 1.3 terahertz. At low frequencies between 100 GHz and 300 GHz, we see a roll-off, a rather sharp one, of characteristic of 1 over f square, where the beam is fundamental Gaussian to begin with at lower frequencies. And as you can see, the beam is well defined with a main center lobe. As you go along on the frequency, this well-defined pattern starts disintegrating into many lobes, and these lobes completely disintegrate into multiple lobes at around 300 gigahertz. So beyond this frequency at around 400 gigahertz, we reach a plateau where we begin to see a new pattern start emerging. And this pattern starts taking shape as we go along this roll-off. You can see that at 450 gigahertz, it is becoming more and more denser. And towards 700 gigahertz, we can see a fully developed mode, which looks like an annular type beam, which has got a minima at the center, surrounded by the strong emission. Now, as we can see at frequencies going above 800 gigahertz, this is becoming more and more prominent. However, the emission is now becoming more and more asymmetric, meaning that the hole is shifting towards sideways, and the maxima is going on the opposite side. One additional feature that we see here is this side emission at an higher angle, around 25 degrees. We see that present in all frequencies above 450 gigahertz, and this becomes more and more intense. In fact, at higher frequencies, it is as intense as the strong emission in the center of the beam pattern. Now, what means is that if such a beam is not been treated at the very end, at the very beginning, this might lead to some spurious reflections or spurious signal coming from the sideways and going outside the sample under test and returning back to the detector, leading it to false signals. And this can be a problem for a spectroscopy system because your system can no longer be relied because of such spurious reflections or spurious signals arising from such sidewall emissions. So the key takeaway here is that the source must be investigated and calibrated properly before implementing it into dynamic spectroscopical systems. And furthermore, another key takeaway message is that such a insights can only be obtained through imaging, and only performing spectroscopy is not going to get rid of the errors that could arise as systematic errors. So yeah, so as we showed here in this work that the CMOS based camera can be really useful for performing imaging and spectroscopy at the same time. And this can lead to less error prone measurements and get us one step closer to practical applications of terahertz spectroscopy. Thank you very much.